Hello everyone and welcome to the third part of our topic on Strand 3.1. Here we are going to be learning about a redox titration. This titration is similar to an acid-base titration in terms of the usage of the glass vase and calculation. However, it is different from an acid-base titration in terms of the chemical equation. So we are going to be learning the experimental procedure of how to do the redox titration, as well as we will learn how to do the calculation of the concentration of the oxidant and the reductant. A redox titration is similar to an acid-base titration because the same equipment is used. The two chemicals that are involved in a redox titration are known as a titrant, which is a reagent of known concentration and volume that is used. And the other one is called the analyte. It is a chemical which is undergoing the analysis. So this is the one that we are interested in finding the concentration of. In a redox titration, there is absolutely no compulsion in using an indicator. Unlike in an acid-base titration where an indicator was compulsory, if a redox titration involves a noticeable color change, then there is no need for an external indicator. However, if the titration does not involve a noticeable color change, then a redox indicator may be added. So one of the redox indicator that is frequently used is starch. Starch is used to show tiny amounts of iodine that is present in the titration, and this is used whenever the titration involves sodium thiosulfate. So in a sodium thiosulfate titration, which is going to be second stage titration, which we will be learning later on, we are going to be using a starch indicator to show the color change. When the starch indicator is added, there will be a drastic color change starting from brown to bluish black, which will eventually turn to colorless. A primary standard is a solution which is used in a titration, and this solution is anything that has a known concentration. Some of the very commonly used primary standards that are used in titrations are potassium permanganate, oxalic acid, potassium iodate. So these are some of the common examples of the standard solutions that are being used. In most of the titrations, potassium permanganate is a very common primary standard. And the reason why it is used very frequently is because of the following reasons. It is a strong oxidant. It can readily oxidize most of the reductant, such as Fe2+, oxalic acid, iodide ions, thiosulfate, and many more. It is readily standardized. To standardize, it is titrated with another standard solution, and then the exact concentration of that particular solution is determined. So the standardizing agent that is used to standardize potassium permanganate is oxalic acid. Now, if oxalic acid is not used to standardize a potassium permanganate, what will happen is potassium permanganate, since it is a strong oxidant, it will greatly get reduced by sulfur dioxide in the air. So to prevent that from happening, oxalic acid is often used to react with it. The third property and reason as to why potassium permanganate is so frequently used in titrations is because it involves a definite color change from purple to colorless. And this will happen only if the titration is carried out in the acid medium. When we use potassium permanganate in a titration, we do not have to add an external redox indicator. There will be two types of titration that we are going to be studying this year, and these are one stage and a two stage. So let's see what these two stages of titrations are and how we are going to figure them out from our calculation, whether they are one stage or two stage. Calculations in a redox titration as well as any other titration involves four-step procedure. So let's look at the four steps that are involved in doing the titration calculations. Step number one, determine the overall redox equation. And this can be done by balancing the equation either in the acid medium or in the basic medium. Second step, determine the moles of the primary standard using N is equal to CV. So when you read the question, it is very important to highlight certain information. One of the information that you have to pick for is the standard solution. The chemical whose concentration is given will be the standard solution. So you will have to pick the concentration as well as the volume, which will help you to calculate the moles. From the moles of the primary standard, we will be able to calculate the mole of the unknown reactant, which is our analyte that we are trying to study. And this can be done by using a mole ratio to find the moles. So once we find the mole of the analyte, we can use concentration is equal to N over V to find the concentration of the unknown reactant. So let's look at one example that will involve a one-stage titration. So question number 1, how will we determine whether this calculation is involving a one-stage or a two-stage? When you read this question, this is a trick. When you read the question, you have to find how many reactants are there. So in this case, when we are doing the calculation, it says here, calculate the concentration of a 20 ml solution of sodium oxalate. The sodium oxalate contains oxalate ion. So that's our first reagent. We put it into a flask that reacted with exactly 22.4 ml of a solution of a 0.0204 moles per liter acidified potassium permanganate. So that's our second reactant. So in the question, if you have two reactants, that's our one-stage titration. Our first step of the calculation is already done here, where the overall equation is already balanced. Okay. Now, our second most important thing that we have to do is to write and jot our information down. So let's see what are the things we are given. So this is the formula of oxalate ion. Whenever oxalate ion takes part in a reaction, it will get itself oxidized to carbon dioxide. Okay, so for oxalate ion, we know the volume, 20 ml will be changed into liters. And for the permanganate ion, that's coming from the potassium permanganate, we know the volume, which is 0.0224 liters, and we know the concentration, which is 0.0204 moles per liter. So once this information is out, we can very easily pick what is our standard solution. The standard solution is potassium permanganate because we know its concentration. So now we are going to move on to step number 2. Step number 2, we are going to calculate the moles of the primary standard. So the mole of the primary standard can be calculated by multiplying concentration to the volume. So the concentration and the volume of permanganate will be multiplied together, and we get the mole of permanganate ion as 4.57 times 10 to the power minus 4 moles. Now our objective is to calculate the concentration of the oxalate ion. Okay, and to do that we need to know the moles of the oxalate ion. We already know the volume, we just have to find the moles. So to find the moles, we will now move on to the third step. In the third step, we will do the mole ratio between permanganate and oxalate ion. And if you have a look at the mole ratios, you can see the coefficient, the number in front. For permanganate, it is 2 moles. For oxalate, it is 5 moles. So what it basically means is that for every 2 moles of permanganate, there will always be 5 moles of oxalate ion reacting. Now we're going to put that in a mole ratio. So this is how a mole ratio should look like. This is our third step. 2:5. Okay, that 2 means 2 moles of MnO4 minus, and 5 means C2O4 2 minus. So now from our step number 2, we already know the moles of permanganate ion. So let's put that up. We know the mole of permanganate ion. We need to find out the mole of oxalate. If 2 moles of permanganate reacts with 5 moles of oxalate ion, then 4.57 10 to the power minus 4 moles of MnO4 minus will react with how many moles of oxalate? That's what we're trying to figure it out. Okay, so we do the cross multiplication. And when we do that, this is what we end up with when we simplify. So 4.57 10 to the power minus 4 is multiplied by 5. And then that is equal to 2 times x. If you make x the subject of the formula, you will have the whole thing divided by 2. Okay, so here we find out the value of x. X is a mole of oxalate ion. Okay, so that's what we are doing here. And then the mole appears to be 1.14 10 to the power minus 3. So now that we know the mole of oxalate, we know the volume of oxalate, we can find the concentration of oxalate ion. The formula is C is equal to N over V. So the mole of oxalate we found up in step number 3 divided by the volume, which is 0.02 liters, and the concentration appears to be 0.06 moles per liter. So these are our 4 steps involved whenever we do our titration calculation. So let's cross check the steps one more time. We have step number 1, our balanced redox equation. We have step number 2, mole of the primary standard. Step number 3, mole ratio to find the mole of the analyte, which is our secondary standard. And then the final step, C is equal to N over V, where we are using this formula to find the mole of the secondary standard. There are some titrations which cannot be carried out directly. That means we cannot have one reactant in the conical flask and the other in the burette and allowing them to react directly. For these kind of chemicals which cannot be directly reacted with each other, there is a two-stage titration carried out. So what happens here is one of the chemical is in the conical flask. That chemical is treated with another reagent. So whatever product is liberated in the conical flask will then be titrated with a second reagent in the titration. Now the reason why the two chemicals, which is an oxidant and reductant, they cannot be reacted directly is because of this. First of all, the chemicals which are involved in two-stage titrations are iodate ion and bromate ion. Whenever these chemicals are involved, a two-stage titration is carried out. So the reason as to why we carry out two-stage titration is because of this. Number 1, when these two reactants, which is an oxidant and reductant, when they are directly reacted with each other, the equivalence point cannot be determined easily. That's one problem. And the second problem is that if these two are directly reacted with each other, they may end up forming a product. And that product may end up interfering with the thiosulfate ion, which is one of the reactant in the titration. Okay, so we do not want to have this kind of problems arising in the titration, which will give us an inaccurate data. To avoid that, we will carry out the steps in a two-stage. So the first stage that we are going to be doing is this. The chemical, one more time, that we are reacting here is iodate or bromate with thiosulfate. So that is those are our reagents, iodate and thiosulfate. But we cannot react the two directly up. So what will happen is the iodate will first be reacted with iodide ions. And this reaction is going to produce iodine. Okay, so we will have a conical flask in which we will be having the iodate ions. That's one of the reactant in the titration. To this we will be adding some iodide ion that is mixed in sulfuric acid. So when these two react together, they will give you a brown substance which will be the liberated iodine. And this is the reaction that takes place in the first stage. The formula IO3 minus reacted with iodide ion, giving you iodine gas. Now, if you look here, you can see that this equation is balanced in terms of their charges. There is no need to add the electrons anywhere. Okay, so 1 mole of iodate will react with 5 moles of iodide, and to balance the equation, 3 oxygen can be balanced by adding 3 moles of water, and the 3 moles of water will then be balanced, the 3 times 2, which is 6 hydrogen, can be balanced by adding 6 H plus on this side. So when you add the charges, it will come to a 0 charge on the reactant side and a 0 charge on the product side. So how you remember how to balance the equation? It's very simple. Just remember the mole ratio between iodate and iodide. Okay, so iodate plus iodide is giving you iodine gas. Iodate 1, iodide is 5. Okay, just remember the mole ratio and the rest you will be able to follow up easily. So let's see what's going to happen to this liberated iodine that is produced in the first stage. Now the second stage of the titration will involve the liberated iodine being titrated with the sodium thiosulfate. This reaction is going to liberated which is the I2 produced in stage 1, will now be reacted with the thiosulfate. This thiosulfate is going to change into S4O62 minus, while the iodine is going to change into I minus, which is iodide ions. Okay, so we will have to balance this equation by following the redox method we learned earlier on. So let's see how this titration steps is carried out. So in the conical flask, which contains the liberated iodine, okay, the burette containing the thiosulfate, when this thiosulfate is reacted with the iodine, there will be a color change. Okay, and that color change will be that the brown color of the iodine is going to fade to a pale yellow color. So when the pale yellow color is seen in the conical flask, then a few drops of starch indicator is added. When the few drops of starch indicator is added to this conical flask, there will be a color change from bluish black to a colorless solution. So this is how the transition of the color changes when we do a two-stage titration involving iodide and thiosulfate. Now once the titration is carried out, okay, we will now be combining stage 1 equation and stage 2 equation together. So this is our equation from stage 1, where iodide in the conical flask reacted with iodide to give liberated iodine. This iodine was then titrated with the thiosulfate from the burette, producing iodide ion and S4O62 minus. So now once we add these equations up, we will have to cancel the iodine. When the iodine is cancelled out in titration, it simply means it is used up. That is why the color change was from bluish black to colorless. Okay, colorless appeared because iodine was totally used up at this stage. So now if you look here, you will see that the first stage is having 3 moles of iodine, while the second stage is having 1 mole of iodine. So to cancel the iodine altogether, we will have to multiply this equation by 3. And when we do that, this is what we end up with. 3 moles of iodine plus 6 moles of S2O32 minus, giving you 3 moles of S4O62 minus plus 6 moles of I minus. Okay, so once we reach up to this stage, cancel everything that's common on both the sides. Okay, so we will be left with 1 mole of iodide here. Cancel the iodine, right? And then whatever remains, we'll just bring them down. So now let's look at our mole ratio between the two reagents. For iodate, what is happening to iodate? Iodate is getting reduced to I minus. Okay, so when iodate is getting reduced, iodate is acting as an oxidizing agent, while S2O32 minus is getting oxidized to S4O62 minus. So S2O32 minus is the reducing agent because it's getting oxidized. Okay, so these are the two reagents that we are going to be using in the titration calculation now. So now let's see an example of a two-stage titration calculation. When we compare it to the one-stage titration calculation where we were given 2 reactants, here we are given 3 reactants. One is the potassium iodate, the other one is the iodide ion, and the third one is the thiosulfate ion, which is S2O32 minus. So you have to remember the table of oxidant and reductant and know which reactant is changing into what product. So let's say, for example, when iodate reacts with iodide, the product will be iodine. And when this iodine reacts with a thiosulfate, which is a S2O32 minus, it will result in the formation of iodide ion and the tetrathionate ion, which is the S4O62 minus. So now let's pick our important information. We already have our balanced equation here where we have the 2 reactants. We have the iodate ion and we have our thiosulfate ion. Okay, so we have the volume of potassium iodate 20 ml. We have the concentration of potassium iodate, which is 0.01075 moles per liter, and we have the volume of our next reagent, which is the thiosulfate, and that's 27.45 milliliters. So these are the only information we need. Now let's put them together. So the first step will be to find the mole of the iodate, which is our primary standard. We will follow the same 4-step calculation. Okay, so the mole is equal to CV. The concentration is 0.01075 multiplied by 0.02, which is the 20 ml in liters. And the mole of iodate comes to 2.15, 10 to the power minus 4 moles. Using this, we will now go to the third step, which is our mole ratio between iodate and thiosulfate. So the equation, you will be able to see what our mole ratio is. Okay, our mole ratio is 1:6, right? So now we're going to put that mole ratio here, and then the mole of iodate ion, which we found to be 2.15, 10 to the power minus 4, is to X. So this X will be the mole of thiosulfate ion. Okay, we'll just work this out, solve it up, simplify it. It will read as 2.15, 10 to the power minus 4 multiplied by 6, which is equal to 1x. So making x the subject of the formula, this is what we have. So the mole of thiosulfate is 1.29 times 10 to the power minus 3 moles. And once we know the mole of thiosulfate, we can easily find the concentration of thiosulfate. C is equal to N over V. Okay, so just have to substitute our values, and our answer should be written in 2 decimal places, which is 0.05 moles per liter. Finally, let's have a look at the experimental procedure in how the 2 titrations are carried out in a 1-stage and a 2-stage procedure. So we will look at the first example, 1 stage between potassium permanganate and ferrous ion.
Determination of concentration of KMnO4 solution using oxalic acid. Titration is a common laboratory technique used to determine the unknown concentration of a given solution. In this titration, the strength of the given potassium permanganate is determined by titrating it against standard solution of oxalic acid. In the reaction between potassium permanganate and oxalic acid, permanganate ion is reduced to manganese 2 ion in the acidic medium and oxalate ion is oxidized to carbon dioxide. Our aim here is to determine the concentration of a given potassium permanganate solution by titrating it against standard solution of oxalic acid. Materials required: oxalic acid crystals, potassium permanganate solution, dilute sulfuric acid, distilled water, electronic balance, weighing bottle, spatula, 250 ml beaker, 250 ml standard flask, 250 ml conical flask, glass rod, funnel, test tube, dropper, 50 ml burette, burette stand, 20 ml pipette, and hot plate. Procedure: preparation of 250 ml 0.1 molar standard solution of oxalic acid. The weight of a solute required to prepare a standard solution is equal to the molarity of the solution into molecular mass of the solute into volume of the solution in liters. Here, molarity of the solution is 0.1 molar. Molecular mass of the solute oxalic acid is 126 grams per mole. Volume of the solution is equal to 250 ml, that is equal to 0.25 liters. Therefore, the weight of oxalic acid required is equal to 0.1 into 126 into 0.25, that is equal to 3.15 grams. Place the weighing bottle on the electronic balance and tare the balance. Using the spatula, take oxalic acid crystals and transfer them into the weighing bottle and weigh 3.15 grams. Transfer the weighed quantity of oxalic acid into the 250 ml beaker. Wash the weighing bottle 2 or 3 times with distilled water to transfer the particles sticking to it into the beaker. Dissolve oxalic acid crystals in the beaker by gentle stirring with a clean glass rod. Using the funnel and the glass rod, transfer the entire solution from the beaker into the 250 ml standard flask. Wash the beaker, glass rod, funnel and funnel tip 2 or 3 times with distilled water to be certain none of the solution has stuck to the equipment and that all solution has been transferred to the standard flask. Carefully add enough distilled water to the standard flask to reach just below the calibration mark. Add the last few drops of distilled water with the dropper until the lower level of the meniscus just touches the mark on the standard flask. Stopper the standard flask and shake gently to make the solution uniform throughout. The molarity of prepared solution of oxalic acid is 0.1 molar. Determination of concentration of potassium permanganate using standard solution of oxalic acid. Take the burette, rinse it with distilled water and drain the water. Repeat this process 2 or 3 times to drain out the impurities from the burette. Then pour a small volume of potassium permanganate solution into the burette through the funnel, rinse the burette and drain out the solution. Repeat this process 2 or 3 times to remove any moisture inside the burette. Use the funnel to fill the burette with potassium permanganate solution to just above the 0 mark. Take the beaker and place it below the burette and slowly open the stopcock so that potassium permanganate is allowed to run out into the beaker and set the initial burette reading as 0. Clamp the burette vertically in the burette stand. Take the 20 ml pipette out a small volume of distilled water, rinse it and drain the water. Repeat this process 2 or 3 times to remove the impurities from the pipette. After rinsing with water, pipette out a small volume of oxalic acid solution, rinse the pipette and drain it. Repeat this step 2 or 3 times to remove any moisture inside the pipette. Now pipette out the oxalic acid solution from the standard flask until the solution level is just above the calibration mark on the pipette. Close the upper end of the pipette with the index finger. Slowly release the finger so that the solution is allowed to run slowly until the lower edge of the meniscus just touches the mark on the pipette, so that the volume of the solution becomes 20 ml. Carefully transfer the 20 ml oxalic acid solution into the clean conical flask. Touch the tip of the pipette with the bottom of the conical flask to transfer the remaining solution from the pipette. Now add about 20 ml, which is the test tube full of dilute sulfuric acid, to the oxalic acid solution in the conical flask. Place the flask over the hot plate and heat the contents of the conical flask to 60 to 70 degrees Celsius as the reaction takes place at a higher temperature. Place the conical flask on the white surface of the stand under the burette to correctly view the color change. Run potassium permanganate solution dropwise from the burette into the conical flask with constant shaking of the solution in the conical flask. Continue till the color of the solution changes from colorless to light pink on addition of the last single drop of potassium permanganate. This is called the end point. Note down the final burette reading and repeat the same procedure until concordant values are obtained. Record the observations in the tabular column. Calculations. Volume of oxalic acid is equal to 20 ml. Molarity of oxalic acid is equal to 0.1 molar. Volume of potassium permanganate solution is equal to 16 ml. From the reaction between the oxalic acid and potassium permanganate, it is clear that 2 moles of potassium permanganate reacts with 5 moles of oxalic acid. According to the molarity equation, volume of potassium permanganate into molarity of potassium permanganate divided by volume of oxalic acid into molarity of oxalic acid is equal to number of moles of potassium permanganate divided by number of moles of oxalic acid. That is 16 into molarity of potassium permanganate divided by 20 into 0.1 is equal to 2 by 5. Therefore, molarity of the given potassium permanganate solution is equal to 20 into 0.1 into 2 divided by 16 into 5, which is equal to 0.05 molar. Molar mass of potassium permanganate is equal to 158 grams per mole. Therefore, the strength of the given potassium permanganate solution is equal to molarity of potassium permanganate into molar mass of potassium permanganate is equal to 0.05 into 158 is equal to 7.9 grams per liter. Precautions. Always keep the lower end of the pipette in the liquid when sucking it. Carefully fill the burette with the solution and see that the stopcock does not leak. Read the upper meniscus while taking burette reading with potassium permanganate solution. No drops of solution should be at the tip of the burette at the end point. Rotate the titration flask throughout the titration to ensure the uniform distribution of potassium permanganate solution. During titration, operate the stopcock with the left hand and constantly swirl the flask with the right hand.
So students, you have just seen how we are going to standardize a potassium permanganate using oxalate ion. Once a potassium permanganate has been standardized using potassium or sodium oxalate, the concentration of the potassium permanganate would be determined, and then that potassium permanganate would be used as a primary standard with a reaction with iron. Now let's check out on the two-stage titration. Thank you students for watching the video. I hope you have understood all about redox titration that you need to. Take care. We will meet in our last session of the video where we will be discussing electrochemistry and the calculations behind it. Take care. Bye.